Hello and welcome back. In this lecture, we will move from theory into practice. We've already explored how the Magic Wand application is structured, the accelerometer handler, the gesture predictor, output handler, and the detecting gestures loop works. Now, this is the big question. How do we actually get this application running on a microcontroller? That's where we come to the next stage, deploying the Magic Wand to microcontrollers. When we talk about deploying a machine learning model to microcontrollers, we have to remember that these devices are resource constrained. Unlike your laptop or smartphone, which have gigabytes of memory and powerful CPUs or GPUs, a microcontroller may only have a few hundred kilobytes of flash memory and tens of kilobytes of RAM. Yet, with careful optimization, we can still run deep learning models in real time. The tool that makes this possible is TensorFlow Lite for microcontrollers, often abbreviated as TFLM. This is a special version of TensorFlow designed for extremely small devices. It takes a trained model, usually in .tflite format, and allows it to run directly on embedded hardware. The process usually looks like this. First, we train the model, often in a computer or in Google Colab. The trained model is then converted into a TensorFlow Lite model. This makes it fit into small memory. The model is then quantized, meaning the numerical precision of the weights is reduced, usually from 32-bit floats to 8-bit integers. This shrinks the size drastically without losing much accuracy. Finally, the model is compiled into the firmware and uploaded onto the microcontroller. Once it's deployed, the microcontroller can run interference on incoming data with minimal latency, making the one responsive in real time. And what's great is that TFLM is compatible with multiple hardware platforms. In this project, we'll focus on the Arduino Nano 33 BLE Sense, but it also works with boards like SparkFun Edge, which is designed for ultra low power applications. So, deployment is not just about copying files, it's about carefully converting, compressing, and integrating the model into the hardware environment. Now, once the model is on the microcontroller, we want to make sure it runs smoothly. This brings us to the next important step, optimization. There are several techniques used to optimize TinyML applications. First comes quantization. As we discussed, this reduces model size and RAM usage by converting floating point weights into integers. For example, a 20 KB float model might shrink to less than 10 KB after quantization. This not only saves memory but also speeds up computation. All then comes efficient buffer management. Remember our accelerometer handler? It needs to manage a buffer of sensor data. By carefully cleaning and reusing this buffer, we minimize memory overhead, ensuring the device doesn't run out of RAM. Then comes threshold tuning. In the gesture predictor, we can adjust probability thresholds and the number of consecutive confirmations. Tuning these values helps balance between accuracy and responsiveness, reducing false positives while keeping latency low. Platform-specific optimization. Not all boards are created equal. For example, the SparkFun Edge is designed for always-on listening and ultra-low power consumption, while the Arduino Nano is more general purpose. By tailoring parameters for each board, we can get the best performance. And lastly, the code efficiency. Finally, because microcontrollers don't have operating systems or large processors, Even our code structure matters. Using lightweight functions and minimizing unnecessary computation that keeps the application responsive. By applying these techniques, the Magic Wand project achieves what seems impossible: real-time inference, low power consumption, and reliable recognition on tiny devices. Now let's talk specifically about the Arduino Nano 33 BLE Sense, since that's the board we'll be using in this course. The Nano 33 BLE Sense is built around the NRF 52840 MCU, which is a 32-bit ARM Cortex M4 processor with floating point support. It also includes Bluetooth Low Energy, making it great for IoT applications. Most importantly, it comes with built-in accelerometer, which is exactly what we need for gesture detection. No extra sensor modules are required for this reason, so everything we need is already on the board. It's also compact, low power, and designed for always-on ML applications, making it a perfect fit for this project. And of course, it integrates seamlessly with the Arduino IDE, so the development process is straightforward even for beginners. Now let's walk through the steps of actually running the Magic Wand example on your Arduino. First, you will need the following: a Arduino Nano 33 BLE Sense board, a micro USB cable, the Arduino IDE installed on your computer. The Magic Wand example is a part of the Arduino TensorFlow Lite library. To install it, open the Arduino IDE, go to the Tools menu and select Manage Libraries. Search for Arduino_TensorFlow Lite and install the latest version. Once installed, you will find the Magic Wand example under Files, Examples, Arduino TensorFlow Lite, Magic Wand. Once you open it, you will see multiple tabs with source files. The main tab corresponds to main function.cc, which is the entry point of the function and the program. Before uploading, make sure your Arduino Nano is selected on the ports manager and the correct COM port is chosen in the port menu. Once that's done, click the upload button, the right facing arrow in the IDE. If everything goes well, the code will compile and upload to your Arduino. After initialization, the LED on your board should flash to indicate the application has started. Now comes the fun part. Open the serial monitor. From the Tools menu, you should see the message Magic starts. This means the wand is ready. Hold the board in your hand as shown in the instructions, with the components facing upwards and the USB connector pointing left. Now let's try performing gestures. The easiest one to start is wing. Swing your hands quickly, taking about 1 second to complete the motion. If successful, you will see the red LED illuminate and the output in the serial monitor. Congratulations, you have just cast your first digital spell with the Magic Wand. It may take a few tries to get the hang of it because the model was trained with the board mounted on an actual wand, but with practice, you will be able to perform wing, ring and slope reliably. So to wrap up this stage of the course, we have seen how the trained Magic Wand model is deployed onto microcontrollers using TensorFlow Lite for microcontrollers. We have learned about the optimization techniques like quantization, buffer management, and platform-specific tuning that makes real-time inference possible on devices with limited resources. We have also got familiar with Arduino Nano 33 BLE Sense, the main platform for this project, and walked through practical steps of running the Magic Wand example in the Arduino IDE. Most importantly, you have now seen the complete journey from raw accelerometer signals to real-time gesture recognition, and finally to user feedback using LEDs and output. This shows the true power of TinyML even on a tiny board. we can build intelligent interactive systems that respond instantly to human input. In the next section of the course, we'll move beyond using a pre-trained model and actually learn how to train our own Magic Wand model. This means collecting data, pre-processing it, designing a CNN, and optimizing it for deployment. By the end of that stage, you will not only be able to run the demo but also customize the wand to recognize your own gestures. So, with that, let's move on to the exciting world of training your own Magic Wand model. So, that's all for this video. Thanks for watching.